So, hi everyone. I'm here with Corrado Pezzato. Thanks for joining us on the podcast, Corrado.
Thanks for inviting.
You just as a short introduction that you can also build on later. You're a PhD candidate in self-adaptive robotic architectures in Delft in the Netherlands, so pretty close to Amsterdam. I guess everything in the Netherlands is pretty close to Amsterdam. Um, you've been doing your PhD for 1.5 years, and you recently also finished kind of a paper that you put on archive. And I think we will talk about that and like the details of what you've been working on in some detail. And apart from that, maybe we can just take a step back and look at robotics in general. Do you have a favorite movie with robots in it? Do you think any of the movies that you've seen so far got it right to any degree?
um, well, it depends what you want to describe, right? So it's it's plenty of movies and robotics, robots in movies, and I think each of them is just addressing a different aspect of robotics. So if you ask me, is there a movie that basically includes everything about what we can think of robotics? I think there is probably none out there.
Mm.
Um, there is one movie that it's actually a cartoon that it's probably the one that remind like stayed in my memory the most is actually the giant iron,
Okay.
and it's very very old, and it's if you want, I don't know if you watched it,
No,
but it's really this giant iron basically that um, lands on the earth. And well, there is a whole bunch of story, and then the friendship with a human, but also humanity was seeing that as a threat, even though this giant machine was actually not harmful, but they made that machine harmful because of the environment that it landed in. So it's a very interesting movie. So
so which aspect of robotics does it address that you find like particularly appropriate?
and I think so the key message or idea that I have is that technology per se is not harmful, or it doesn't have really these um, it's basically the meaning that we give to technology and how we use technology that defines its outcome. So a lot of movies that are like, okay, robots are taking over the world and they're going to destroy humanity, but it's actually humans that are actually designing robots, and they're deciding what's their goal and what's their purpose, and it's basically humans that decide if to use them as weapons or if to make them harmful. So I think this is a pretty interesting aspect of the movie, and also it reflects on how probably society, and not really robotics engineers because they have hands on what's happening, but how society see um, robotics in general.
Hmm. Maybe we can get back to the ethical implications of robotics at a later stage. But before that, maybe you can give like a personal account what brought you into the field and how you ended up being a roboticist.
So I can start way back. So when I was really young, I actually wanted to be a crazy scientist. So I think at this point I kind of managed to get crazy, probably also kind of scientist. So I'm working on that. But anyway, what brought me here, I always liked building stuff, and especially seeing things moving, actuating, and doing things in the real world. So these brought me, it chose my high school that was kind of in this direction. And the first project I did was what, 10 years ago, more, yeah, 10 years ago. And it was these RoboCup competition. So we had to build our robots, it had to follow some line, avoid some obstacles, and trying to find a victim that had to be saved. So this was my first actually approach to robotics, and I guess the rest just came naturally. So, and it's also a lot about chances and opportunities that came along the way. So I'm Italian. I studied my bachelor in Italy, And all of a sudden, a friend of mine just told me when we were approaching the end, hey, you should look into this university here for the master. And this was at TU Delft. And I said, you know what, that looks cool. So I think I might apply. And that's how I ended up in the TU Delft. And yeah, at the end of the first year, we had to choose the thesis that we wanted to pursue in the second year of the master. And also in here, there was a bit of, I was unlucky, but I was also very lucky. And this is for two reasons. So I got unlucky because of the method. We at that time they had to choose to select the supervisors basically. So we were a lot of students and there were a few supervisors. Um, so could actually just express preferences on the projects or the topics that we wanted, and then we basically um, had to get assigned to someone. And unfortunately, I was among the 10 that couldn't get assigned to any topic that was on our interest. So I had to look around by myself because I said, yeah, I really want to do something in robotics and in this field. And so, and this is how I bumped into my former supervisor, who's also my supervisor now for the PhD. And he had this cool project of, bridging and bringing this neuroscientific principle of active inference that was only on paper by then um, to actually real robots. So the project sounded really cool, and I was really excited, and so I started doing that, and I really enjoyed the process of getting to know, the whole active inference and applying that to robotics. And at the end of the thesis, that went also very well. Um, Another opportunity came up that was continuing basically with a PhD in the same group, and I also took that chance. And well, here I am, basically still doing robotics since some time.
Yeah. So I think this is a nice offers us a nice opportunity to move towards your current paper and maybe to get more into the details of how this neuroscientific theory of active inference that we've also talked about previously on this podcast relates to robotics, and like how robotics maybe also can provide us with a tool to test out theories we have about neuroscience by following the guiding principle of you can only understand something if you can build it, and robotics being the field of like neuroscientific abstract theories of cognition coming really to fruition to some degree. Um, so maybe to I think there's several places we can start. Maybe we can start off with this general problem of short-term optimization and long-term planning that we encounter in robotics, I think especially, and what kind of different approaches exists right now in the field, and what makes this problem so difficult to tackle.
Yeah. So um, you just talked about this short-term decision making and the longer-term planning, and well, we can actually divide or describe the robotics community in two big categories, at least for the sake of this explanation here. So we have the people taking care of actually making long-term plans. So this is actually the classical good old-fashioned AI basically. So you want to describe the world with symbols, and you want to have some heuristics to reason upon the symbolic world that you have, such that if you have a long-term goal, then you can come up with a policy or a sequence of actions such that you can complete the task. And this is usually done at the symbolic level. And by symbolic level, I mean, for example, if you have the task of emptying the table, from dirty dishes, then you might find a sequence of actions, which is pick up dish one and then place it on the tray, pick up dish two and place it on the tray, move to the kitchen, open the dishwasher, fill the dishwasher, and turn it on. So this is the first level of um, the first group, basically, let's call it, or the level of planning that I'm talking about. And then there is another one, which is actually, okay, how do you execute uh, in practice these actions? How do you pick up something? And in this case, you have a shorter term planning, let's call it, because you need to decide online on the moment what your motion should be, and how to coordinate your hardware, if we're talking about robotics, such that you can achieve the goal that you planned before. So where is the problem? The problem is that, well, we're actually really good at planning at symbolic level. So this is a field that has been explored since, well, 30, 40 years or so. So we're really good at that, right? But there's actually a problem when you want to move from the symbols to the actual motions, and especially if these motions are in the real world. So it's very hard to come up with an architecture which is capable of doing um, both the long-term plan, but also the short-term planning or actions and adaptation. Because yeah, when you move to, especially to the real world, then nothing really goes as you planned. So this also motivated my well, the initial work that I've been doing for my PhD was, okay, since the planning problem is basically solved for the kind of situations that we're trying to address in robotics. So I'm working for with mobile manipulators basically. Um, since this problem is more or less solved, how can we take, plans that we did, so long-term sequences that we planned offline, and how can we execute them reliably? So, and this is more or less what we do every day. So, whenever you want to do something in your apartment, since now we're all in quarantine, um, you probably have a high level, idea of the things that you have to do for doing, I don't know, go and brush your teeth. Um, but then a lot of things can change if you're moving from your living room to the bathroom. Like the door might be open or might be closed. Maybe the toothpaste ran out, and all these kind of things that you cannot really um, take into account beforehand. Otherwise, you would just sit, on your sofa thinking for 200 days. Okay, what's the best, or what are all the possible outcomes that I might be, I might possibly do to actually go and brush my teeth. So no, you just have a high level idea of what you want to do, and you just start executing, and you adapt your actions as you're on the go, basically. And this is exactly the idea that I had for the paper. So have a set of um, sub goals and then try to move from one state to the next one, just trying to find your way.
Hmm. I think one of the issues with this symbolic approach to AI is that the world is not a place to be like fully planned out, fully understood, but it's like a stochastic, statistical world full of uncertainty. I think that's probably one of the big realizations of neuroscience, like a lot of people in the last couple of years, that really this uncertainty is not only, it's kind of more a feature than a bug to a degree, because it allows us in the brain to select very flexibly when we are encountering uncertainty. And maybe this pandemic is a good example, because not a single person for really was expecting the year to go the way it actually went. So we definitely need to have this cognitive flexibility, and like in terms of evolutionary history, it makes a lot of sense to, if we go back to the way our lives probably were back in the savannah, then you have a lot of uncertainty constantly. So you need to be a very adaptive robot, so to speak.
Exactly.
So
And
maybe we can, yeah.
no, no, go ahead, please.
No, I was going to move towards like what you did in your paper, but if you have something.
Oh no, I was just saying, okay, if if I had my initial plan since I started high school, then I wouldn't probably be here right now, because a lot of the things that happen actually changed my initial plan. And even if maybe the final goal is the same, then, well, I took some different paths, and this is what brought me here. For example, so this also level of adaptation, it's something that you see also in your longer term planning. If you think about, okay, where do you want to be in 10 years or something? So it's always a dynamic process, and I have to say it's very random. So we shouldn't be afraid of including stochasticity and all the randomness in our algorithms. And yeah, instead of trying to model everything perfectly, we should just embrace the fact that uh, things might happen uh,
Hmm.
and we cannot do anything about it.
Maybe that's also like one of the hallmarks of what we consider to be a really intelligent behavior, because intelligence is kind of this ability to act intelligently in a lot of different environments, and that also counts for flexibly being able to shift our behaviors when environments suddenly change. So I think we can also in the end talk more about this meta question of what intelligence actually is and how that relates to robotics. Where we can go at this stage a bit into the details. We're starting out with behavior trees and how they implement the symbolic behavior, and how that now then kind of what you
Yeah,
did to alleviate some of these problems.
yeah. So I'm gonna start reverse. So from
Mm.
the final goal, and then we can work back to the initial use of behavior trees. So um, the problem that we have is that if we take into account that the word is stochastic and uncertain, and if you would like to actually have planners that can handle all the possible contingencies in the world, then you would end up in some combinatorial explosions of your states, and it's not really computable in a decent amount of time. So since the problem we're tackling are, yes, in dynamic environments, but we more or less know the boundaries of the capabilities of our robot and the kind of things that might possibly happen in the environment to some extent, then we can still take into account some stochasticity. So things might go wrong or they might go not as we planned, but we can also try to sort of model the behavior of a robot such that it can compensate for some of these uncertainties. And well, behavior trees are actually a very nice way of modeling behaviors, or behavior trees for a reason. And they came from the gaming community. So they were first developed for NPC, so non-player characters in video games. And that's also something that really fascinated me. So how actually is the AI behind characters in a game be developed? Because sometimes they seem really smart. So this is one of the technique which is used to specify behaviors, um, and it's quite powerful, and it gained popularity in robotics in the past 5 years. And it's very easy to use, and it's basically just a graph, a directed graph, in which you can specify the behavior of a robot. So in this situation, you should do this. In this situation, you should do uh, that. So why is this useful for robotics, or at least for the task planning problems or task execution that um, we're talking about? Is because it gives a first layer of what we call reactivity. So whenever you have a long-term task and you do a plan to solve the task, then you have your policy. And since we're considering situations in which action might fail or they might be repeated because maybe the robot dropped something on the way, etc., then you would like to have a system which is capable also of repeating some actions or skipping them if they're not needed. And this is exactly what a behavior tree does. So it encodes the solution for a task, um, and this solution is reactive to the changes in the environment. And and this was quite interesting to be actually applied in robotics, especially for our case, because first of all, it's quite intuitive, and this is not to underestimate when you want to make things in the real world. And second of all, it was a nice way um, to integrate with active inference, which is the other part of my work.
Yeah, but I guess one of the issues with behavior trees, as you describe it, is really that you have to a priori account for all the unexpected things that can happen. So you are not really robust against unexpected things too that are happening,
Exactly.
or like the
So
unknown unknowns. So you kind of
exactly.
have to. It probably is kind of focused on like pre-specified limited environments. As you say, video games are probably a good example where the developers really have this closed system of possible actions, possible outcomes, and as soon as you move to like more complex things, you don't really have a way of dealing with situations where that then doesn't
Yeah.
work.
So, and that was exactly the point of extending these to have a more powerful decision making. So exactly as you said, okay, how to handle unknowns, and because the unknowns you might be able to tackle them, with pre-programmed behaviors. If this happen, do this, or according to this variable, do that. But what if you don't even know what can go wrong? So,
Hmm.
and there you see the limitation of these techniques. And also planning in general, because when this happens also in the more good old-fashioned AI, then your system just fails. And what you do is usually you update the state of the world. So something changed. Okay, I update my knowledge about my understanding about the world, and then I replan. So I come up with a new sequence of actions. I really didn't want to do this. First of all, because from a conceptual point of view, you're not throwing away uh, all your plans of a lifetime if something goes wrong, right? So it's probably easier to just shape them around the contingencies that happened. So you can, temporarily move away from your initial plan, but you should still keep in mind the goal that you wanted to reach. So to solve the unknown unknowns, I actually wanted to use, I think active inference was a nice framework to actually encode these more advanced adaptation to things that do not go as expected. Because this is actually one of the core ideas behind active inference, right? So we're acting in the world such that we can minimize the difference between what we want and what we actually have. So this was nice, to combine with behavior trees.
Yeah, maybe we can take a step back at this point to give like a short introduction into what active inference and free energy is and how this relates to what we've been talking about already, like the question of uncertainty and acting, these kind of
Yeah.
things.
So you talked with Charles, and well, he's also here at the TU Delft at 3ME, and he also tried to tackle, okay, and trying to give a definition, very simple, about the free energy and active inference. Um, I would like to give a definition which is closer to what the paper is also tracking. So with active inference, it's, well, with free energy principle, but also active inference, if we include actions, is this beautiful, at least in my opinion, it's very beautiful idea of combining, um, if we say that in control terms, state estimation and control. Um, but let's make a step back, otherwise we go too much into the technicalities. So let's say that you are an agent, right? And let's say that you have an internal model of how the world should evolve. And this model can actually be biased towards your desires. So let's say that you have a certain idea about the environment in which you have, and you have a certain idea also at regarding basically how you would like the world to look like. So you have this model here, and what free energy and active inference do is basically trying to minimize or actually maximize the evidence of your model such that it matches the environment, and at the same time you want to act in the environment such that it matches your desires. Um, so yeah, this is what basically active inference does. It tries to first of all make sense of the world, and second of all act on the world such that it complies to your desires.
Yeah, I think this is a really important point about active inference in general, or maybe also robotics in general, that really in order to act meaningfully in the world, you need to have some kind of implicit model of how the world could behave in the future to come. So if you, especially if you want to build long-term actions and make meaningful decisions in the future and implement them, you need to have some kind of understanding of how things could become and things could be. And I think in implicitly in behavior trees, you also have this world model, the model of the world that incorporates all of the things that could happen. But if we want to really get to that more flexible point, we need to have more abstract working models of how the world could be. And
Yeah,
then along them, you make basically predictions about the outcome of your own action.
exactly. So the key that it's missing, for example, in behavior trees is that for example, in active inference, you try to minimize future values of the free energy, for example, when you want to act on the environment. So your action selection is not dictated by what the designers did beforehand, before starting the task, but you choose actions such that your free energy will be lower in the future. And the free energy is based basically on the model that you have about your environment. So if you minimize the free energy, you're also making the environment comply to what you would like to have.
Yeah, and this active component is really something I think that is best understood in the context of robotics, actually. So yeah, how does this active component come in? Maybe just
Yeah.
go
So
into.
um, the active component, exactly. Well, it comes in when you want to. So you can do two things basically. If you're an agent or a robot, you can basically, if you're trying to use the free energy principle and active inference, you can do two things. You're always trying to minimize one single cost function, which is the free energy. Um, and you can minimize the cost function in two ways. So you can, first of all, try to make sense of the world. So you have some sensory input, you're sensing something in the environment, and you have an internal model, and you try to build an internal representation of the environment. So this is the first way you can minimize free energy, basically estimating the world. But you can do this up to a certain point, because the model that you have inside contains also your goals and your desires. And if these are not already present in the environment, then if you don't act in the environment, there is no way you can further reduce the free energy. So this is where the actions actually come into play. So you can use actions to change your sensory input. And this is something that puzzled me at the beginning, because it's a different way of actually seeing control. So you're doing control to change the things you're feeling, and such that your feelings are matching your internal idea of how the world should look like. And I think it's a really interesting and fascinating idea of putting down the problem.
Yeah, I think it also nicely relates to this whole inside out approach to the brain versus the usual outside in approach. That it's really the brain is not only an organ that perceives the world abstractly, and then you expect something to happen, and if it doesn't happen, you have to kind of yeah, adjust your model of the world and of how things are. But you can just then get up and make it be
And
the
do.
way you want it to be. And yeah, it makes a lot of sense, just very pragmatically from an evolutionary perspective, that we are machines. Or I mean, I don't want to like de-romanticize human beings, but we are agents in a world that are trying to, yeah, act in the world in order to survive. Like thinking doesn't have any. There's no point to thinking unless it serves the purpose of leading kind of the meaningful action.
Exactly. And also, like, uh, what are the what's your goal? I mean, what do you want to achieve? I think this is a pretty interesting question to answer, maybe in the future, in a couple of years. Because
Mm.
usually what we do in robotics is, okay, you have a task to solve, so the programmer or the algorithm is just trying to solve this task. But it's basically us giving the goal. But who's giving the goal to us in a more philosophical way, right? So why do we do the things we do? Um,
Mm.
that's very interesting.
Then it gets even more complicated. Like to have that faculty of giving ourselves goals. Like, or it seems to be the case.
Yeah, exactly. Because so from the free energy principle, it all starts from the fact that organisms, they want to survive, and in order to survive, they need to minimize the surprise, which is or surprisal, which is associated with their sensory readings. Um, and then it's very beautifully derived, the whole free energy principle and active inference, from this single idea of surviving. And that's also something that really caught my attention at the beginning.
Yeah. So yeah, how how do you combine behavior trees and active inference in your framework? Like, how does it work?
Yeah, it's actually to give desires. So it's to give these priors, which are basically describing how the world should look like. So to give you a very simple example, how people used or designed behavior trees at the beginning was to command actions. So if you want to exit your room and the door is locked, then you might have a behavior which is approach the door. If the door is closed, then open the door and then traverse the door, right? So this is the classical way of having a behavior tree and how it describes a behavior. Um, and I remember it was last year, I was sitting in the office and thinking, okay, but do we really do that? I mean, when I'm thinking about going out the room, do I really, plan this sequence beforehand? Do I plan the actions, or do I actually plan the observations that I would like to have? So you can see the same problem, which is going out from the room, from an observations or a sensory input perspective, as active inference does, which is you would like to have yourself outside the room and you would like to see the door open, right? So the way I use behavior trees to encode uh, desires is exactly this one. So I encode the observations that the agent would like to have in order to complete the task. So I don't give actions anymore, but I just give desires. And then I let the active inference try to make sense of the world, but also make the world comply with what I specified. So if the behavior is okay, you would like to have the door open, then when you run online the active inference, then well, if the door is already open, then you're happy. So the free energy is minimized and you don't have to take any actions. Whereas if the door is closed, then there is a mismatch between and the current state and the state you would like to achieve. So you try to act in order to minimize this difference, and well, most likely will be opening the door. And this works well because, well, what happens if there is a very annoying guy in the office that is shutting down the door after you opened it? Um, well, there is not really a problem in that. So because the observation changed back, and then you're still trying to having the door open, so you just attempt again the action. So um, and this all seems very easy and nice in active inference, but if you try to actually encode actions in a typical way in a behavior, then you would need to have a lot of if then or a lot of hand coded recovery to actually have this behavior. But yeah, I just delegate that to active inference and it's taking care of making decisions online.
Okay, so on the micro level, basically the active inference algorithm tries to figure out the best actions to lead you towards that goal.
Exactly.
Maybe we can at this point also talk about this idea of hierarchization, because I think this is also crucial when it comes to how to implement long-term goals, because pretty much everything in life really decomposes from this highest layer of I want to be a researcher in 10 years to I need to do my PhD, I need to finish this paper, I need to put my hands on the laptop, something like that. So yeah, how does it actually work from your perspective in robotics? How does this hierarchization work?
Yeah, so usually historically you have these three layers architectures, they're called. So you have the first layer, which is the most abstract, the one in which you take decisions about what to do in the long term. Then you have an interconnection layer, let's say, and then you have the low level layer, which is actually executing the motions in the world. Um, and um, this is more or less how the majority of the works, in robotics, divided the problem. Um, and this also kind of relates to my work. So um, you have this high level layer or the more abstract layer, which is the one taking symbolic decisions. And since you want to actually have things working in the real world, sometimes we need to rely on uh, engineering and architectures that actually allow us to bridge this high level decision making that we're doing with the actual motions. So in my work in the paper, these well, the architecture goes as follows. So you have the high level decision making, you have the ROS infrastructure. So ROS is the robotic operation system, and which is taking care of basically handling the communication. And the lowest layer is actually your controllers. So these actually get the goal, which is, I don't know, moving to a specific configuration, and they just execute the motion. So this is the level of hierarchy that I have in my system, for example, but it's quite a common one when you want to have these long-term execution of tasks in the real world.
Yeah, I think that we can also relate that to neuroscience to a degree. Probably robotics was also inspired by neuroscience in the way this is structured. That you also have in the brain this hierarchy of like the brainstem or this motor area, mainly cerebellum, these kind of areas, and on the upper level you have the prefrontal cortex. That's kind of the operating like long-term planning, and then that gets implemented into the body. Maybe in some level I think these analogies also break down because it's sometimes not as clear cut.
Yeah, there is. So as you, I like this part. Like there is, not a clear cut, and this is also one of the main uh, well, I wouldn't say problems, but hot points or hot questions when you want to build systems. Where do you draw the line? What do you consider a certain hierarchical level? How many levels of hierarchy do you consider? How do you split the problem such that you have the best outcome? So it's not really clear where to draw the line and what to consider in one level or in another level, basically.
Maybe one example is also this muscle memory idea of us having to really focus with our all of our attention and cortical might on fulfilling a certain task when we start learning an instrument, but at one point it becomes so automatized that it really moves out of the reach of the like the cortex doesn't need to be involved anymore, but really have within the nerves that are responsible for the motor actions, they take care of most of the things that can, like most of the problems that can occur basically.
Exactly. And that's really beautiful that we can actually manage to do that.
Yeah, it's also very useful. Otherwise you would have a hard time surviving in this world.
But that's also, so this is one criteria that is also used in robotics for drawing the line. So as I told you at the beginning, then we have these different communities or different hierarchy and layers, and one is taking care of planning and the other one is taking care of executing, for instance. So if you want to draw the line somewhere, so for what things do you plan and for what things do you actually execute, in feed forward, blindfolded, um, your actions. And one criteria is that you can do that for actions that basically, or routines or policies that never change. Then you can just have a fixed structure. You don't need to do any higher level planning if the sequence to do something is always the same. So you take some burden from your cognitive and system and your thought processes, and you delegate that to actually these hardwired um, behaviors that, well, they work. So why should you bother just spending time thinking about them?
So is there a lot of coordination in the robotics community? Because it seems that you mentioned this robot operating system, that a lot of the movements, for example, are probably pre-planned or someone figured out how to do them best. And then can you just download some kind of library to move your robot around in space or something? Or how does it work?
Yeah, so some of the problems are, uh, well, I'm gonna be careful here at saying solved, because yeah, we don't see still robots around. But anyway, we can find solutions reliably to some of the problems. Um, so for those, there is no need of using, super complex algorithms uh, to do everything basically. So you can break down the problem. You can use, so the ROS and the robot operating system is nice because you have a whole community of developers who's dedicated to advancement in robotics, and you might have some packages that you can just download, and then they do localization and mapping, for example. So you can just pull something, and then you know where your robot stands in the environment, and you can also at the same time create a map of the environment such that you can give some goals and navigate. So you can basically reuse um, parts of pieces of software that are actually working, and just neglect the details about the implementation. So in my opinion, it would be really, really hard to just try to, I think it's impossible, try to solve everything from scratch or with a new paradigm
Yeah.
without reusing things.
Yeah, it's probably also the way evolution does it, just reusing most of the stuff that already works like on a lower level and then building it up to more complexity. This is probably a very sensible way to go about it. So you are also like really implementing these things within a robot. So what kind of tasks can you do with it, or how does like an experiment that you do look like?
Yeah. So the one that I use also for the paper is basically so I'm part of Air Lab, which is the AI for retail lab, and I'm working with four other PhDs in Delft, and each of us is doing something different on the robot. So I'm working on the task planning and execution, and another PhD is working on the motion planning. Another one on developing skills for grasping object, which is still a huge challenge, even if it doesn't look like, but it is. And two others, well, one working on the ethical side of the development of robotic systems, and another one working on multi robots and coordination and routing. Um, So I actually forgot what I was saying at the beginning. Um,
What
but
kind
the
of
task that, yeah,
experiments?
sorry,
Yeah,
the experiments that, sorry, I got carried away from um, the main goal, you know. Anyway, um, so the kind of tasks that we're trying to solve are actually within these retail stores. So we have a fake supermarket, and we have our mobile manipulator, which is just a base that can move around, and there is a robotic arm on top. So we assume that, well, we can sense something from the environment, for example, where some objects are, and we also have some prior knowledge. For example, in the left corner there is the milk, and in the right corner you can find the cereals, for example. So the robot has these kind of information available, and the kind of tasks that we're doing is, for example, okay, move to these box, for example, pick up the apple and bring the apple to the customer. Or some other things. So the longer term goal is for the robot to be able to autonomously, restock shelves when they're actually empty. Um, there are some advancement in that also in our lab. So you can have the robot which is reasoning about, okay, when the shelf is actually empty, and how can I place objects such that I can refill that. So we can do that in a lab basically. Um, yeah, so these kind of tasks basically. So they're mobile manipulation tasks in which the robot can navigate, interact with the objects, picking them, placing them somewhere else, and all of these basically autonomously.
and the goal is then to integrate all of this into an agent that could potentially also be used like really in supermarkets or maybe Amazon storehouses or something like that.
Yeah, so this is probably not something we're going to achieve by the end of our PhDs, but it's probably the longer term vision. Um, but I'd say it's not really to have a product. It's not to develop a mobile manipulator to deploy in the supermarket. So this is just the use case that we have, um, which is a good one because if you consider supermarkets, then they have a certain structure in them. So you have that probably the vegetables are always in the same place, and the fridges are always in the same place. But at the same time, you also have all the variability and all the troubles that comes with the fact that supermarkets are designed for humans, and there are humans in the supermarket. So you have both. You have some structure that you can leverage, and you also have all the uncertainties that come with the fact that you're operating in a space which is designed for humans. So the goal actually is to investigate how you can actually integrate these solutions that can interact with the environment and with the people. um, yeah, and what are the problems that you encounter with that? So where are the limitations of the current research, and how you can advance that? So that's I think, a better way of posing the overall goal of the lab.
So can you answer the questions that you just posed yourself, which is like
um, we might have. So if I had the answer, I'd probably be done with my PhD, right? Um, but we have some approaches. So and some fundamental core issues or ideas that we would like to investigate. So, and one of these is, just to give you an example. So there is a lot of literature in robotics for trying to avoid collisions. So robots are bulky and dangerous, so we want at any cost to avoid any collision with the environment. And this is how, well, things have been developed, uh, mostly in the past years. But when you want to really have robots to do things in the real world, then you might need to allow some collisions. So you might bump into something, you might need to push something, you might need to interact in a more um, well, aggressive is probably not the right word, but you get the point. So you need contact. So one problem that we need to address is, okay, how do we allow contact, still maintaining all the safety around the interaction that we have with the objects, the environment, but especially with the humans. And so that's one research question, which is not really an answer, but it's at least a direction for where to go.
but it also be makes sense to implement it in terms of like a prior of not wanting to have any contact with human beings, so kind of being discouraged from states where you have contact with persons.
Yeah, exactly. And yeah, and other problems are really, we don't really know what are the problems. So this is probably the main idea, that since we don't have really data or experience on how actually robots interact in environments that are designed for humans, then the first problem is finding out what are the problems. So, and this is something that is coming probably in some years, when we will have solutions that are actually working in environments which are for humans.
But it's also very exciting stuff. It's actually the robots coming to live and work among us. Maybe
Yeah, because like the idea that we have is that robots are behind cages doing things super fast and super precise. Um, and yes, this is what happens in industry. So if you go to some production lines for car manufacturers or um, other production lines, it's really impressive how robots move, super fast, super precise, and um, but that's a controlled environment, right? So what's really exciting is, okay, let's have a smaller, safer version of these bulky robots, and what do they how do they behave in an environment which is designed for us and not for them? And that's really exciting.
yeah, it's funny that I had an interview recently that one of the inventor of the robot that drives around cleaning dust away it was really the first robot that was actually made a lot of money. So it was made sense to commercialize it because it was really an application that made sense for a lot of human beings. And it was in a sense also the prototype of what you just described of a robot having to like invade the space that is really shaped for humans and not for robots, and kind of make sense of that environment flexibly and try to do
Yeah.
its task, and probably like, yeah, cleaning
And then
dust.
imagine stepping up from that, instead of having, a round base which moves around, um, try to put arms and try to interact with the objects. That's a whole next level. Um, it's it's super fascinating, in my opinion.
So how far do you think we are in general? Like, what's your prognosis for how soon we will see these kind of robots around us pretty frequently?
So um, I think in here we need to be a bit careful, answering this question, because we can see robots among us. I mean, you probably have clear examples, this yellow dog walking around, doing stuff super gracefully, or some other robots, doing flips and backflips and dancing. Um, but where is the catch? So probably we're very close, with the mechanical, with the hardware, basically. So we can have systems that can move gracefully, that can be really competent, right? But usually these systems are either teleoperated, so there is a human behind a computer, just, or a joystick, just driving the robot around and making it do very crazy stuff, or they are basically the highest expression of control theory and how we can actually make machines follow trajectory and act, basically. But the catch is that all the intelligence comes from the operators and the programmers. So most of the intelligence, basically. So I think we're very close from the hardware perspective to have robots around doing things, but we're really far on the cognition capabilities and intelligence.
So now that you mentioned intelligence and saying that most of the intelligence comes from the operators, what is intelligence for you in this context, and maybe more specifically applied to what you also do in robotics?
Yeah. So $1 million question
Yeah.
of what's intelligence. I think there is not really one specific answer, but I can give you my view about what an intelligence system is, and especially for robotics. So when would I consider a robot uh, intelligent, right? So in my opinion, and it's probably looking a bit far ahead in the future, is that, well, I consider something intelligent, uh, when a machine is capable of taking decision autonomously, learning continuously, and taking rational decisions in the environment. um, so I mean, you touch some parts of definitions of intelligence, creativity, curiosity, memory, and like all these things. I think they should be probably included in the definition of intelligence, even though I don't really know to what extent or exactly how. But for me, an intelligent robot is something I would be impressed of. Let's put it that way.
Yeah, maybe. Yeah, I think there's, yeah, different layers on which we can be impressed, like in terms of like chess computers, for example. AlphaGo was also something I found extremely impressive, but it's still this constrained space. So I think, yeah, intelligence in terms of the generality that makes our human intelligence so special. Maybe that's another thing.
Yeah, and probably to also to add a bit on that. Um, so I think, especially nowadays in robotics, we're trying to solve practical problems, and we are finding solutions for some problems. So we make things to work. Basically, we make things work. Um, but there is a difference in between making things work and actually having true intelligence. So you can find solutions for a problem, but it doesn't mean that you unlocked, you know, what we all want, or well, supposedly want, which is general artificial intelligence, and that would be probably the final goal. So not a specific solution for a problem, but uh, just solving artificial intelligence, and that would be the first intelligent robot, probably.
Well, I think what you are doing is actually kind of a nice kind of underscores in which direction the field is moving and in which ways it could be moving towards more generally intelligent things. Because if you start off with behavior trees, like a system that is carrying out search on a behavior tree doesn't seem very intelligent to us because it's already everything is already done by
Yeah.
human operators. And I think that's probably what you mean when you say that. Like these Boston Dynamics, these crazy dancing robots, everything is pre-programmed, and that's really not more impressive than a car, except that maybe we have figured out some components of movements. And what really makes intelligence so special is to move towards this more flexible selecting actions based on things that we haven't really accounted for in advance and really have this cognitive flexibility probably. I think maybe we can also talk at this stage about this inside out perspective because we we have discussed this book in our
Yeah.
monthly meetings quite a lot because it also ties in with this whole idea that intelligence might be in some way related to actions, and intelligence can only be meaningful if it's grounded in some kind of actions in the world. And I think robotics is really tackling the issue. And maybe this could indicate that robotics is really the way to go if you want to understand intelligence better.
Well, for sure, you're gonna get a lot of insights on what the problems are when you want to do things in the environment. Um, but yeah, so um, maybe to so because let me rephrase that. So um, robotics is a field that started back in the 60s. You had these very old robots, the shaky robot that was navigating somewhere and reacting to the environment. So we have a long history of robots, actually. And back then it all started with these good old-fashioned AI, so symbols. Let's describe the world and let's make sense of it and reason upon it. And these in recent, in the last 10 years, these completely lost interest because we actually realized that okay, we can think about the world, but we cannot do anything. So the robots were really dumb in the sense that the skills that they had to interact with the environment were really limited. And then the whole deep reinforcement learning and deep learning approaches to actually cope with the complexity of the real world, and they came into place. So now we're pretty good also at having single skills. I'm super good at opening the door. I'm super good at picking up this mug. Okay, so and then what is the problem that we're facing now then? Which is, okay, we have a lot of single skills that we don't really know how to connect or how to transfer um, to different tasks. So probably now the time is ripe to combine, the good old-fashioned AI and the symbols with also the skills that we have and some more powerful algorithms for deciding what to do, such that you can have systems that are more capable, basically, and they cannot only do one single thing, but they can do a variety of things, and you don't need to retrain networks or simulate thousand millions of episodes to be able to act.
Yeah. Yeah, it seems that some of the properties are like the features of our brain, like attention, for example, is really also a tool to organize on a global level, integrate a lot of different things we are specialized in into one cohesive framework. and,
Exactly.
and also to figure out where to look for information. I think this is also a cool feature that comes out of the free energy principle to a degree, because
Yeah.
attention is also yeah, so,
So the whole exploration exploitation dilemma,
yeah,
right?
yeah,
And this comes nicely within the free energy principle and active inference, because since you describe your problem as maximizing the evidence of your model, then you intrinsically have a trade-off in between exploring the world and having a more goal-directed behavior. So you don't need to have these tricks or hand-coded heuristics to decide when it's time to explore and when it's time to act. But since it's all balanced into the free energy, then you can take care of this dilemma automatically. So it's a very nice way of solving this problem.
Yeah, a popular critique of the free energy principle is sometimes that if you want to minimize surprise, you can just hide yourself in a dark room forever, and if you don't have any inputs, you're not going to be surprised. But maybe to answer that from the exploration exploitation perspective.
Well, like at some point, that's really the argument, against that. But I remember Friesen, also Carl Friesen, developing the theory and answering these um, critics, or um, yeah, basically saying, okay, at some point, if you're sitting in a dark room, you might get thirsty. At some point, you might get hungry. So it's not the absence of sensory input doesn't necessarily mean that you're not going to act, basically, because you might have prior desires such that you still want to do something to be happier, basically.
And you don't only have a model of the world, but also a model of yourself, and that model of yourself is you as being someone that's not thirsty. Then you
Exactly.
definitely need to at one point act on this.
Exactly. And it blends very nicely with the fact that you do everything in order to survive, right?
Yeah, I think that's the idea, that you have these kind of representation of yourself, and it's also part of your model of the world that you are surviving. It's like the
Exactly.
most crucial model of the world, and you want to kind of, from the perspective of thermodynamics, keep yourself from dissipating away, which you would do if you don't pay good attention to yourself. You just dissipate.
Exactly. So you want to stay in a non-equilibrium, right?
Yeah, it's
If you reach the equilibrium, then you probably did something wrong on the
yeah, you probably die. So
way.
this is suboptimal solution. Uh, yeah, I think we talked about already about how to get from this robotics perspective on towards like the human perspective, and to understand how our brain might do the things that, or like tackle the most important issues in robotics as well. And I think, yeah, the free energy principle really nicely connects robotics and neuroscience. And just one thing I thought about a little bit is this current trend around this atomic habits in the self-help literature, and this habit stacking, and all of these ideas around building habits being extremely useful way to increase our productivity. And do you have any thoughts on how this approach to habits might relate to what you're doing in robotics as well?
Yeah. So mm I think this connects a bit with what I said before, that for some things we don't really require to do some complex planning or thought processes or reasoning, right? So um, if you know that every time to pick up this bottle, you need to approach it from the top and then grasp it, then there is no reason why you should to try very different, or to try to learn different policies, or to try to reason about very different ways of doing the same thing. So in robotics, we might have habits which are these things that uh, they work 99.9% of the cases. So and these are basically the things you tend to neglect at some point, because you say, okay, it always works in mostly all the cases, so let's just have the hard-coded habit for the robot, and just think about the other problems. So this is probably how habits can come into robotics. um, but on the other hand, I think it's a bit different in the sense that probably also that 0.01%, it's very interesting. So if you end up in habits, then you might miss out very interesting things. Um,
Yeah, this
yeah,
reminds me of the central issue in self-driving cars is that the 0.01% leads to lethal accidents. So you can't get away with leaving that in and automating it. So it's really the details can matter greatly. It also reminded me of this silly example of jellyfish that at one point swim around the ocean, and if they found a nice place, they just chill down on a rock and digest their own brain. So because they kind of, it's funny from this inside out perspective, you don't need a brain if you're not planning to act anymore. So like acting flexibly probably takes up most of our cognitive resources. So just automating a lot of things and kind of trying to build a model of the world that works most of the time is one of the central goals. But
Yeah, exactly. So like having habits, it's very efficient if you want to do things. I'm also like on a on a human level, it's you get things done when you have habits, and you
yeah,
just don't think about it. You do it, very efficient, very nice. Um, but on a more philosophical way also, if you're stuck with your habits, that's a problem because you might just hang around in your comfort zone, right? And you might not explore different parts of life. And from a robotic perspective, you might not explore different parts of your state space. And maybe they're better, but if you're stuck with your habits, then you'll never know.
yeah, it's interesting how in human beings it also shifts. Like people in their 20 are lacking habits, and maybe they only have bad habits of getting drunk during the week and being hungover, but at least they are more creative about it. And you can see this kind of decline in creativity is pretty stark actually when people move past their 20s. But then like if you think of the workload of people like in their prime, in their 50s, like professors or something, the things they can handle just because they just figured out how to do things properly for a long period of time, it's actually also
Yeah.
very useful.
So there is a balance, right? So you
Mhm.
shouldn't get stuck in just habits, but you shouldn't also get stuck in just wander around and try out different things, because that's not very effective. So
Yeah,
probably the truth is in the middle, right?
yeah, or like the useful thing about societies is that we can have like some Gaussian distributions over these attributes, and we can have people on the edge that are extremely creative. And like being extremely creative means you have a lot of terrible ideas and some good ideas, and then most of these people with these terrible ideas just fail horribly, but some of them have really good ideas. And the more habit based, like less curiosity driven people can just make society function properly.
Yeah.
So maybe if we build like populations of robots, we can also like distribute some of those properties nicely.
Yeah. Or you can just delegate all the boring stuff and
Yeah.
then focus on the more creative ones. Because I mean, why do you build habits in the end? Like, what's the purpose of building habits? It's because of having a lot of things done in a very short period of time, because you probably lack time.
Mhm.
um, so if you can delegate some of the things that are habits or tedious, then you might have more time to be creative and still get things done.
Yeah, this also relates to the ethical aspects of where robotics could take us, and AI is going to transform society in general. I don't know if you have opinions on that, but kind of this issue, as you just said, we are planning or hoping to automate most of the boring tasks and most of the boring things away from our lives, but then everyone is kind of required to be very creative and
Yeah.
innovative
So
about the way they
people,
live.
yeah,
Yeah.
like some people like to do boring stuff. Like, I'm happy with my job doing my routine, and then I like it, right? I'm talking about like a hypothetical case. um, so yeah, we should be careful not to uh, replace. So that's the key point. What we're trying to do is not replacing, but it's just helping and aiding. So I think there is a difference. And if you develop systems carefully, and you instruct people, um, and educate people, um, then I don't see much problems, let's say. So it depends always, as we said at the beginning, how you use technology. And I think a lot of good things. Um, Technology can bring a lot of good things, and we just need to use it carefully.
And are you worried about where AI could move Like these, a lot of people are warning about where AI could take us and possibly endanger our species.
Yeah, so I don't think the current state and the state in 10, 20 years probably is going to be a threat, and not even in longer terms. And the fact is that um, basically a machine or an AI doesn't intrinsically have a goal. I mean, it's not a biological system that wants to survive at all costs. So it's always up to the designer to give some goal and some meaning to what the system has to do, basically. So um, so why would an AI want to overtake the world, basically, if this was not instructed by a human? So again, it's up to us basically to be careful and to think about the consequences of what we're doing.
Do you think at this point, when we are starting to develop techniques where this kind of these goals are given to the AI system by itself, and we just specify the state it wants to obtain? I mean, there's this example of the paperclip maximizer that you probably also have heard
Yeah.
about, where it's really from the free energy principle perspective, you specify the end state of you should have a lot of paper clips.
Yeah, exactly. But in the end, you also so I'm a practical guy, right? So I build stuff, and um, a lot of these fears and um, bad thoughts, they come from the fact that think about everything as virtual. But to really have an impact also on our society, we need physical things, physical robots and physical stuff. And as every physical object, then there are limitations. So you can argue on a theoretical level that, on a theoretical level, you can go to infinity. But on a practical level, you might die before you can reach, from here to 80 years. So um, yeah, theoretically might be possible to have something that can do everything in its power to achieve something, but on a practical level, you smash your head against the limits of the physical world.
Yeah, and then that system, if we get close to building one and it gets out of hand, we probably notice early enough that it won't destroy everything. I think, yeah, us without us noticing to build something as powerful that it can just wipe out mankind by building paper clips. As I mean, it's a thought experiment, but it seems yeah, sometimes as you say, thought experiments go to infinity just in one step, and engineers have a different perspective on this.
Yeah, I mean, we have already the possibility of wiping out humanity, right? So
Yeah,
we
true.
have nuclear weapons, and I think that's far more dangerous at this stage, at least in these years, than just it's a good mental process to think about these things, and we actually have to do it, in order to foresee futures and anticipate that, such that like bad things don't happen.
It's also a product of our own free energy principle in action.
Yeah,
But
I mean, you're
yeah.
gonna act to survive, so in order to survive, you're not gonna develop the things that
Yeah, you need to select good actions, and yeah, building these kind of AIs is a dangerous course. Yeah, but it's so weird because, like as we said, the world is so full of uncertainty that we have a really hard time selecting the proper actions for ourselves and in our own lives. And probably most of the time, we also don't really understand how we select our own actions.
yeah, sometimes, but even on a very simple daily life, I mean, sometimes I just think about the things I do, and they just don't
Mm.
make sense at all. So um,
Yeah.
and that's also connects with some of my ideas or views on the whole branch of um, optimality and optimal control that we have in engineering and in robotics. And if you look at biological systems, then we're probably far away from behaving optimally at every time.
Yeah, it's really a stack of good enough. So yeah, that kind of
Exactly.
worked, and just Yeah. Does on a meta level, does studying cognition and robotics make you kind of neurotic sometimes in everyday life, that you becomes hyper aware of your own actions? And
That's actually so. It's I've been trying this experiment with my flatmate, and we decided, okay, we always say, what can robots do with capabilities from humans? So you try to imagine what a robot could do and do this and do that, but what about the other way around? So what can you actually do with the capabilities and the sensing that a robot has? So and it's very funny because if you try to move like a robot and sense like a robot, you can do probably 2% of the things that you do on your daily life. And here you can already see like the core limitations of the technology, and that also helps you understand that, yeah, it's not really a threat at this moment. So if you go home and you try to move like a robot and close your eyes, close your nose, close your ears, and just see a bunch of pixel around, you realize quite soon that it's very hard.
hmm, yeah, that's reassuring. But yeah, so also on the meta level, so kind of what drives you in your daily research? Why do you think you are a scientist, and what?
So uh, it's an interesting question. So what drives me is probably curiosity, and actually uh, the challenge. Like I like to challenge myself in hard problems, and uh, and especially, yeah, as I said, it's mostly curiosity. So understanding the why of things and try to come up with solutions for problems, and to basically, I'm curious about the things I don't know. So actually, what drives me is my ignorance. So that's probably a better way of putting what's driving me. It's my the black uh, um cloud around my understanding of the things that is actually driving me in studying and um, do science.
Yeah, it's funny that uh, I think on a neural level, there's also some evidence that kind of conceptualize this space of the unknown in a way, conceptualized in the brain, and it also, like, from this exploratory perspective of that this is a space to be explored, and you can have that in the jungle, and it could be a place where there's food, but it could also be a place where there's danger lurking. We kind of process with the same neural infrastructure this the universe, for example, and there's this bunch of really highly explorative, curiosity driven people that then turn to science and astronomy, and just they really need to know what's up there in this dark cloud of the unknown.
And also, the more you know, the more you don't know, right? So it unlocks a lot of
Mm,
different topics and theories and things and ideas, and it might be overwhelming also sometimes. But
mm,
uh, it's what drives me, basically, this fact of this idea of exploring the things you don't know.
yeah. And I think once you get into research, you realize that it's not that it's not hard to find something that is unknown. Like, you just start your PhD, and then 3 months later, like, everything is unknown.
It's like what's happening here.
Can anyone help? Nope.
No,
Professor.
anyone? No.
Yeah, yeah. And considering you've spent now 1.5 years of your PhD, and you also did your master thesis, and do you have any advice of, or like, if you think back on how it was for you to determine which field you want to work in, and how much exploration should there be, how much before you decide on a course of action?
So there is no optimal policy. That's my point. So
Yeah.
my advice is try to go out your comfort zone and experience, because the more the better you can understand what you like. So try to be curious, and that helped me. So I moved to TU Delft because I was curious of living abroad and having being immersed in very international environment. And then opportunities came up. So don't be afraid of taking, all the opportunities that come up and pops up um, on the way. And for the rest, like for me, it was a bit easier because I already knew what I wanted to do. So, I like building stuff, and the whole field of robotics is just very inspiring. But maybe for someone else, people might not already have clear what they want to do. But in that case, yeah, just keep exploring, and uh,
Hmm.
things will come to you probably.
Yeah, I think that's a beautiful final message out to the world. And I think we can end it here. Thanks a lot for joining us on the podcast.
Thank you for inviting me.